In today's lecture, we covered pointers and some common uses for pointers. Tutorial 2 in your workbook has exercises related to pointers, and in this presentation, I'll cover the solutions. The full list of topics covered in Tutorial 2 is pointers, memory diagrams, and some practice writing pseudocode. If you haven't already done so, please attempt Tutorial 2 before looking at the solutions. Exercise 1 asks us to draw a memory diagram at point 1 in a small section of C code. It asks us to draw using memory addresses as well as using arrow notation. The first solution I give is using memory addresses, and I assume that the addresses started at 4000. You could choose almost any other number as long as it's a multiple of 4. The reason for that is, on a 64-bit machine, the memory is organized in section of 8 bytes, or 64 bits. If an integer was stored at an address that wasn't a multiple of 4, it wouldn't be possible to store 2 integers in an 8-byte section of memory. So as an example, we have a 64-bit machine which can read 8 bytes at a time, but it can only read at multiples of 8. If an integer was stored at, say, address 10, that would mean that 2 bytes of the integer would be stored in one 8-byte section of memory, and the other 2 bytes would be in a different 8-byte section. In that case, it wouldn't be possible to read the integer using only one memory access. To avoid that problem, compilers will put integers at addresses that are multiples of 4. The way to describe this is to say that variables are aligned in memory. Now back to the diagram. X1 was stored at address 4000, so there's 4 bytes that it requires, so the next address is at 3996. Again, we agreed that addresses would decrease as we add values onto the stack. And recall that we're using 64-bit machines, so the pointers require 8 bytes. That's why P1's address starts at 3984, but P2 doesn't start until 3976. The program assigns values to X1 through X4 initially, and the pointers get assigned to their corresponding variable. So P1 points to the address of X1, P2 to X2, and so on. Afterwards, the statement P1 equals P2 will change what P1 points to be pointing to what P2 points to. So the result of that is that P1 now points to X2, which is what P2 also points to. In the memory diagram, you can see that both P1 and P2 point to address 3996, which is X2's location. The next statement, star P3 equals star P4, those are dereferencing, so they're not going to change what they point to. They'll change the values at that location. So it says the value at P3, which is X3, will be changed to the value that P4 points to, which is the value of X4. So immediately after that statement, both X3 and X4 would have value 40,000. The next 4 statements increment the values that pointers P1 through P4 point to. Notice that since P1 and P2 point to the same thing, the value of X2 gets incremented by 1,000 and 100. And X1 doesn't get incremented at all because nothing is pointing to it. And now I'll show the same diagram except using arrow notation. Here's the memory diagram using arrows, and it's somewhat easier to see because the arrows explicitly show what pointers are pointing to. But you should be familiar with both styles just in case I ask on the exam for one or the other. Now for exercise 2, a good first step is always to look for globals and anything that might appear on the static memory section. And in this case, we actually do have something that would be stored on the static section, and it's the string literal used in the printf statement, \n x equals %d, etc. We'll cover more of that when we study strings. So if you did put that in the static section, that's great. If you didn't, don't worry about it. So in this example, we have three functions active at point 1. Main calls red, red calls blue. And you'll need to step through to see how you get all those specific values. I'll only highlight a couple key points. The first one that I want to mention is that inside of function red, where char m gets assigned, it's assigned the value of star c plus plus. So because the plus plus is on the right, that's a post increment. So m will get the value of star c before it's incremented. So m has a value of 101, and after that, the value that c points to is incremented to 102. And at the same point, I want to point out that we have memory alignment happening again. So m is stored at location 7968. But the next variable, instead of being stored at 7967, since m is only a single byte, it's stored at 7964. Now technically a should be at an address that's a multiple of 8 because a takes up 8 bytes because it's a pointer. But it's good enough to have it at a multiple of 4 to avoid checking if it's a multiple of 8 or not. I guess the quick way to check is to see if any variable that's larger than a single byte is stored at an odd address. That's indicating a problem. Inside of function blue, argument A is passed by address and B is passed by value. So only the changes to A will be seen outside of the function. And we can see from the diagram that A is pointing to X at address 8000. The value at X before calling blue is 102 as a result of the star C++. So the first statement inside of blue, star A modulo equals 10, puts the remainder of X divided by 10 into X. So 102 divided by 10 has a remainder of 2, so the new value of X is 2. The other aspects of the diagram I won't cover here, so if you have any questions, just post on the discussion boards. Now at point 2, we've returned from the blue function, and we're back inside of red. So on the memory diagram, we only see 2 functions now. Not much has changed besides that, except for the value of X is now -5, which is a result of the call to blue returning the value into star C. So the return value from blue is -5. So star C equals -5 is assigning the value -5 to X. And lastly, at point 3, we've now returned from red, so we only have the main function active. And the only change is that the return value from red is now assigned to Y. And the return value from red was 101 plus -5, which is 96. Now let's move on to exercise 3, which asks us to write pseudocode and then actual C code for drawing a type of pyramid or triangle of letters. And the example there is given. Because you're asked to write pseudocode, there's going to be a wide variety of answers, and as I described in the presentation about pseudocode, there's a real spectrum of pseudocode. Some is closer to English and some is closer to code. I prefer writing closer to code, but if you prefer writing closer to English, that's totally acceptable too. The key insight for this problem is that there's really 2 dimensionals of processing. There's one dimension, which is the rows, and the other one is the columns. So the number of rows is determined by the character that gets passed in. Now the number of columns is equal to the current row that you're in. So this has sort of a matrix structure. If you think of the problem for a single row, you have a maximum character just for that row. So if in the example, the maximum character of the third row is C. In order to print characters from A to the current maximum, which is C in this case, you need to use a loop. And once you've figured out how to do a single row, you just repeat it with an outer loop that increases the maximum for the inner loop each iteration. And that's exactly the idea that both of the pseudocode that I'll show you express. The first one is closer to English, and the second one is closer to code. So take a few moments to look at the first one. And now here's the second one, which is much closer to code. In the first line, I have for each outer character, assign the value of a set, which is A to maxchar. Maxchar is the character that the user would input to the function. Inside the set, I use the ellipsis, or the ... to indicate that from the first character A up to the max character, there's a continuous sequence of characters. And it's the same idea for the inner loop. There's a continuous set from A to outer char, which is the maximum just for that row. And here is C code for that function. Both of the pseudocodes would get translated into something similar to this, but the second one would be much easier to convert because it's already fairly close to code. In this tutorial number 2, we saw pointers and memory diagrams, and I also introduced the idea of memory alignment for the first time. We'll see the issue of memory alignment cropping up quite often as we move forward. And in the last example, we had some practice writing pseudocode. So if you have any questions about any of these exercises, please post to the discussion board, and I'll answer your questions there.